Let's continue the conversation about classifying salt-affected soils, but in this video, let's focus on sodic soils. And sodic soils are simply soils that contain high sodium concentrations, and that's expressed as a high exchangeable sodium percentage or a high sodium adsorption ratio. So first of all, these soils typically have pH values above 8.5, and the soil condition just looks poor. All right, you may have polygons on the soil surface where the soil is simply crusted all over completely. There's a white precipitate on the soil surface, would be pretty obvious. These soils have high amounts of sodium, and when high amounts of sodium are present in soils, that causes clays to disperse. What does this mean? This means that the sodium ion, which is positively charged, is attracted to clays. But the sodium ion is huge. It has a huge hydrated radius. If you recall from the lyotropic series that you learned way back when in Unit 4. The hydrated has it has 6 water molecules surrounding the sodium ion itself, and it's huge. And when it gets in between clays, it pushes clay particles apart, which is dispersion. And so instead of having aggregation, which is created sometimes with calcium, which has a +2 charge, which pulls particles together, sodium pushes particles apart and disperses aggregates or causes aggregates to dissolve, if you will. And when that happens, that reduces infiltration of water. It reduces hydraulic conductivity, or the ability of water to move through the soil, and it simply destroys soil structure. So the soil may look structureless. The other issue that you find is that sodium is toxic, and toxicity, especially to roots. So above ground, you may see plants suffering or just completely dead. And if you were to pull a plant out of the ground and look at its roots, it would have shortened, stunted, darker roots. Telltale sign of toxicity. And in this case, it would be sodium that's causing the toxicity or killing the apical meristem, or the growing tip of the root. So at the very bottom of this slide, I share with you the characteristics of a sodic soil. The electrical conductivity is relatively low, less than 4 millimoles per centimeter. All right, so the amount of overall salt is relatively low, but the exchangeable sodium percentage is high. It's greater than 15, and the pH is high. It's greater than 8.5, and the physical condition is just poor. So, like I mentioned on the previous slide, sodium has a +1 charge. It has a large hydrated radius. It causes more dispersion, and even though it's a +1 charge, if you remember about the lyotropic series, right? Potassium has a +1 charge, ammonium has a +1 charge, but sodium has a +1 charge. But sodium, if you go back to Unit 4 and look at the hydrated radius, it's much larger than potassium or ammonium. And so when it moves in between clay particles, it pushes clay particles apart. And so here are 2 graphs that illustrate this. The graph on the left shows you the exchangeable sodium in a soil increasing from left to right, and the amount of dispersed clays on the y-axis from 0 and moving up on the y-axis, increasing. And what do we see in a number of different types of soils is that as you increase exchangeable sodium, the amount of dispersion increases. Relative to that is hydraulic conductivity as compared to the amount of dispersed clays. And so this is one study that looked at 3 different factors. So if we took the y-axis from the graph on the left and made it the x-axis on the graph on the right and looked at relative hydraulic conductivity, so the amount of water that can move into or through this soil, as the amount of dispersed clays increases, the hydraulic conductivity greatly or drastically decreases. Look at the y-axis. It's on a log scale. It drastically decreases. And so there's a direct correlation between exchangeable sodium in a soil and the ability of water to move through soil, or lack thereof. The other issue with sodium in a soil is that it not only, when it becomes toxic, kills the apical meristem, it causes the shrinking of cells within the root itself because water is not being attracted to the root, it's being attracted to the sodium or sodium chloride in the soil solution itself. And so and this is illustrated in these pictures, all right? So as you increase the amount of sodium chloride in solution, it says root reduction occurs. Reduce water and nutrient transport. And that should make common sense to you. If a plant root is supposed to look like this, the top panel, panel A, but it looks like this in panel C, right? So the entire root architecture shrinks simply because of, among other things, lack of water, right? The water is not being attracted to the root itself.